In this video, I'm going to be talking about Maclaurin series, whatever the plural of series is, and some of the identities that you need to know and some of the nuances behind those identities, okay? So, first things first, we have this Maclaurin series. Now, what is a Maclaurin series? A Maclaurin series is simply any Taylor series that's centered at 0. I have a video, link will be down in the description for that, on Taylor series, and went a lot, pretty in detail for what being centered at a series or a Taylor series means. So if you don't know what that is, then go ahead and watch that video. Link will be down in the description. But a Maclaurin series is basically just any Taylor series that's centered at 0, right? And you actually, for some functions, you actually get a pattern that ends up showing up whenever you are trying to expand the Taylor series of this. And these are the identities, Taylor series or Maclaurin series identities, okay? So the first identity is 1 over 1 minus x. It's simply the series of x to the power of n, starting at 0, going up to infinity. And this is what the series looks like. Now, if I were to change this guy just a little bit, maybe change this to 2, then you would get n 2 to the power of n plus 1. If I were to simply change this to 3, then you get 1 over 3 minus x. Okay, it's not that bad. Or the series wouldn't look like this anymore. Okay, so ignore this. But this is what the sequence function would look like for the series. Revert that back. All right, what about e to the power of x? Well, e to the power of x is a very simple pattern. X to the power of n over n factorial. And this is what it looks like as you expand. Okay. If you actually in my previous video on Taylor series, I actually expanded e to the x manually. And, well, this is exactly what I got. So eventually the pattern sticks out to you, where you can actually change up the formula for your Taylor series. Okay, but what if you have e to the power of 2x? Of e to the power of 2x, you can simply just multiply the numerator by 2 to the power of n. Okay, or another thing you can do is technically put the exponential in a parenthesis and put it to the power of n. And what you can actually do is separate this into 2 to the power of n, x to the power of n, right? So this could also be rewritten as 2 to the power of n, x to the power of n, okay? Same for 3. This just simply changes to 3. And if you had some coefficient in front of the e, then you can actually just factor out that coefficient in the summation. So this is a more general formula for it, I guess. Okay, how about for your natural logarithm? Well, this guy sort of looks like this. For your Calculus 2 class, you don't really use this guy too much. Maybe some might use it. I really don't know. Mine did not use it at all. It was simply identity that would be on the formula sheet. But it's alternating, as you can tell. It goes from negative to positive to negative, and it's just x minus x squared over 2 plus x cubed over 3. Right? And the reason why this isn't ln of x, and the reason why this isn't 1 over x, is because, remember, Maclaurin series is centered at x equals 0, correct? Well, for the functions 1 over x and natural logarithm of x, it's asymptotal at 0. There's no point on your function that actually reaches 0, right? There's no point on your function for ln of x and 1 over x that actually reaches 0. So since it's asymptotal, you can't make them at x equals 0. You can't make it a Maclaurin series that's centered at 0, right? Okay, let's move on to the sine and cosine. Taylor series, Maclaurin series expansions, and I'm actually going to show you a pretty interesting identity that maybe you've seen before. So these right here are the Maclaurin series expansions for the functions sine of x and cosine of x. And again, if you were to just use the general Taylor series formula, you would get something that's exactly the same as this. It's just that this guy right here represents the series more with less steps. Okay, let's say. But out of these series, well, okay, here, let's talk about the series first before I talk about the little interesting fact. But these are all alternating. Starts off as at a positive number, ends and then alternates between positive, negative, okay? I'll actually show you this on Desmos at the end of this video, of course, how these look like. But basically, as you keep adding these functions, you just get more and more like the sine and cosine functions, which is, I find, extremely fascinating, whoever came up with this. But maybe you've noticed this, but these kind of look like the e to the x Taylor series or Maclaurin series expansion, right? X to the power of n over n factorial. It's just simply 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth. These kind of look similar, right? These sine and cosine Taylor series expansions actually kind of look similar to this, except that they're alternating. Well, there's a really cool identity or formula that comes out of this, and it's e to the I x is equal to cosine of x plus the imaginary number times the sine of x. And I'll make a video on this using Manum. So I'll make it a little more interesting because this is an interesting topic that I can actually prove to you guys. So I'll use a 3 blue 1 brown animation software to prove this. But I'll cover Taylor series in it, and I'll actually talk about how these Taylor series, when you combine them together and multiply sine by I, you actually get e to the power of ix. Their Taylor series are exactly identical if you add the Taylor series for cosine and I of sine. It's absolutely crazy. Euler, however you pronounce it, he came up with this. And e to the I pi is simply equal to -1, right? So if you were to plug in pi here, you would get cosine of pi plus I sine of pi, which is just equal to, well, I sine of pi is equal to 0, so this actually just cancels out. 0 times I is still 0. So you just get the cosine of -1, which is just equal to cosine of pi, which is just equal to -1. This is a pretty cool thing that you can look at. But let's go ahead and move on to Desmoses. I just want to show you what these look like as you add these functions up. Right here, we have the sine wave. Let's go ahead and write down the Taylor series expansion for this. So remember, this is the Taylor series expansion. Right now, you can already tell that this guy's pretty darn accurate at values near 0, right? It's getting pretty close to the sine of x. Matter of fact, this orange line basically completely overlaps this sine of x function from -1 to +1x. All right, what if we keep going? So if we keep going, 5 factorial, we get this. Okay, it's getting more accurate. X to the power of 7 factorial, plus x to the power of 9 over 9 factorial. And you can already imagine, right, these factorials, or this function right here, as we keep getting further and further onto these Taylor series, we just get a function that's significantly more and more accurate to the sine of x function. So you can imagine that if we were to do this to infinity, this guy would just wave back and forth, back and forth, back and forth. Now, with practicality, all people really need to do for like drawing images is by using this Taylor series up to this point and kind of just copying and pasting the sine wave. Copying and pasting like an entire wavelength. So an entire wavelength would maybe start here to here, right? And you just copy and paste the image. That's probably what some calculators do, maybe older versions of the calculators. But yeah, maybe let's draw one more, right? This is interesting. And it just keeps getting better and better, right? So how about, actually I don't think I need to show you for cosine. I think you guys get the point. But really I just wanted to show you this. This is pretty useful. Taylor series are very good for approximations and engineering. And in physics, or very easy, useful, make it very complicated problems into very easily calculatable functions or calculatable series like this. So as always, if you have any questions, put it in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thank you for watching.